Hello, everyone. It's a dream coming true today. 28 years ago, my brother gave me this book to read. Maybe you can't read it from the back, but this is the French translation of The Ages of Gaia. And I was 14 years old, and I would have never imagined that, 28 years later, I would be speaking here. I didn't read the book. I was 14. I didn't quite understand what it was about. And my brother did a mistake. He explained to me that it was about a hypothesis. And in fact, it's part of that. There is a Gaia hypothesis. But the more interesting stuff, perhaps, is about the fact that there is a Gaia phenomenon. And the Gaia phenomenon is the expression of life at the planetary scale. The basic of the Gaia hypothesis is sometimes expressed as the hypothesis of homeostasis or self-regulation. And one of the common imagery which is used to speak about this self-regulation is the machine, is the regulator. This is the homeostat of HB. It's from the 1940s. But this is a machine, it's a very smart machine, which can regulate its temperature with a series of feedback loops. And Jim Lovelock was himself quite seduced by this imagery, I suppose, because basically he is a physician, but he is also an engineer. And this kind of feedback loop is the kind of feedback loop that an engineer would typically design. And this is his own drawing, which I just photographed from upstairs. And you see some similarities, but also some differences, because again, Jim is a physician, and so he knows about the complexity of the human body. And what we need, and some of the questions which were raised yesterday, is how do we make it formal in a certain sense? How can we claim that there is a living phenomenon and not just a series of feedback loops? And this is the very ambitious purpose of this small talk. Right, we will have to do a little bit of mathematics. It will not be overwhelming, but we need to have a little bit of formality. I'm a physicist by training, not a physician. And so I was milked by a community which has developed knowledge and science by modeling objects with dynamical systems. If you want to study the movement of a car, of a bike, or whatever, you use a differential equation. We know that from Newton and Leibniz and all these great people. One way to formalize this is the following. When you study the movement of a body, you need to define its position, or let's say more generally, its state. And state is designed, and it's expressed by a variable x in this case. And the beauty of dynamical systems theory is that it tells you how the state evolves over time, given laws of evolution and maybe parameters, maybe the weight and the mass of the car or the cycle, and forces. And then so you go from time to time, and so time unfolds, and you know the movement. A lot of our modeling actually depends on this formalism. When we implement the laws of motion in an ice-sheet model, we have a formalism like this one. This is a dynamical system. A lot of econometrics is done today with dynamical systems. In fact, it's a very, very powerful language because all scientists somehow recognize themselves with this formalism. If you are interested in control theory, for example, you have a certain target for a trajectory, and you establish which forces you need to put to keep the system under control. If you are interested in statistics, in bias and inference, for example, you may want to make inferences about the parameters given knowledge on a trajectory and forces. Right. So this, basically, it's an unescapable. Most of our computing, not to say all of our computing, is done with this formalism. However, when you start to study living systems, you may come across different concepts. And this is the three concepts which I will review quickly now. So 3 biological concepts. The first is the notion of anticipatory system. You can read the text. It's mainly for me to remember what I have to tell you, but basically we are anticipatory systems in the sense that we have internal models in ourselves that allow us to predict the future and act to prevent damage or maybe increase future rewards. It's easy to think about ourselves. But to some extent, a tree is also an anticipatory system. A deciduous tree loses the leaves before actually the leaves are frozen, so before it gets damaged. And the mechanism by which it happens is that somehow the model, the link between, in this case, sunlight or daylight duration and losing leaves is hard-coded in the DNA, in the protein structure of the tree, and so on. What is important is that the way this coding works is contextual. And any biologist knows, for example, that the sequence in the DNA is contextual and it will express and will have different functions depending on the protein bath in which it is bathed. There is an imagery going with it. I have to be quick because the talk is only 10 minutes. But for those who do control theory, they are used to this idea that you have an input, a system, an output, and maybe a feedback loop. And so the imagery of anticipatory system goes by actually adding here a model that actually somehow anticipates or runs more quickly than reality to produce action. And there is a lot of mathematics going on with this, but I have to go to the next concept. The next concept is autopoiesis. So this was launched by Mathieu Hanna and Varela in 1980. Sergio Rubin, who is co-author of this presentation, would tell about it much better than I do, because he's a biologist. To me, it's a bit more descriptive, but know that there is also formalism associated with this. So this idea of autopoiesis is that living entities are defined by a boundary. So I have a boundary. I have a skin, eyes, ears, etc. A tree has boundaries. And we can already anticipate, but to some extent, Gaia has a boundary, which is the atmosphere. So the key aspect of autopoiesis is a self-reference, or at least self-feedback loop, self-production between the metabolic network and the boundary, in the sense that the metabolic is key to produce the boundary, but the boundary is necessary for the metabolic network to operate. And the boundary also creates the interface between the metabolic network and the outside. So this kind of mutual self-production is absolutely crucial. So next, the third principle. This one is a bit challenging to me to tell you in a few minutes, but I will do the best I can. This is a formal model designed by the mathematician Robert Rosen in the 50s. And this is what he called the metabolic repair system. And you will see how different it is from a dynamical system. So in a dynamical system, you get this idea that you produce products from inputs based on a forcing. That's the idea. You can extend that to what's happening with a metabolic reaction. I mean, if you have inputs, you have products, and the production of these products may, for example, depends on enzymes or active sites of an enzyme. What happens in a living system is that this system is being closed in a bit of a complicated way, and I will browse through it a bit quickly. So basically, the enzymes get used and somehow damaged by the metabolism and by the metabolic production. So you have a system to repair the enzymes using the products and produce again the enzymes. But what's more, in the living system, you also have to care about the usage of this and the fact that this has wear and tear. So you need another layer. You need a replacement system that reproduces the repair, and so on and so on. And the idea of Robert Rosen, and again, forgive me, I have to explain something in a few minutes that took me 2 years to understand. But this idea is that in a living system, there is a closure. So essentially, you can have the system somehow knows how to reproduce itself. It encodes itself, the information to reproduce itself. And that makes a crucial difference between a dynamical system which is open and the formalism which is associated to this, which would be the metabolic repair system in this case, and which is closed to what he called efficient cause. So now, how do we come to Gaia? And as an anticipatory system, I see that Andy is getting nervous because my time is almost over. But I nevertheless have to go through that. There is a discipline, a bit of a niche discipline nowadays. There is a small community around that who does what is called relational biology. And relational biology is interested in the various concepts which I just explained, the anticipatory system, the autopoiesis, and the metabolic repair system. And what this community is busy with, and I'm doing this kind of stuff with Sergio as well, is to establish formal relationships between these various concepts and also see into what extent they differ from the dynamical system. And basically, you can prove mathematically that, for example, this model cannot be simply implemented as a dynamical system. But what would be relational Gaia? Is basically to tap from these concepts and see whether they are useful for understanding Gaia and manage it. So what are the key concepts that we are interested here? First, there is the duality of material and function. Take this bit of ink, for example, which is written 5 minutes. I could see material on it. It's ink. Maybe it's toxic or whatever. It has it's hardware, if you like. But it's also software. It's signaling me. So it tells me that I should hurry up. So that is a code, which in context means that I have to hurry up. When Tyler, it was Gaia Vince who was showing this picture yesterday of sand going from Africa to the Amazon. You can see it as a mass flux. But for the Amazon trees who get this sand, it can have a signaling function. Exactly because signaling the same way signaling works in our body. Self-reference, and I have not to hurry up really. Functional plasticity, a same signal can have different consequences depending on the context. Causal closure, these are all concepts which biologists, ecosystem specialists know about and which are blind to the physicists. And so the question is, if we manage to show to some extent that Gaia can really be modeled with this concept of anticipatory system, metabolic repair, etc., then we have a good rationale to explain that these various concepts, which are currently overlooked in our modeling and our stewardship of Gaia, could actually be relevant. And I have to stop here, I guess. Oh, yeah, there is. Thank you very much.
So thanks for the really interesting talk. So with regard to applying some of the biological concepts to Gaia, what are your thoughts with regard to the following, that some of these biological concepts are developed within living things that are subject to life and death, kind of evolution of those living things, because they can end as whole systems, and therefore the concept of function really comes in. Whereas to Gaia, which is now something larger, it's consisting of evolutionary systems, but it is not itself an evolutionary system. What's the relation there in terms of applying these concepts?
One thing that threatens a living system, and when it is itself in default of anticipation. So if, for example, I come to a situation which I cannot forecast because I'm not equipped to, my life can be in danger. And so the question is how first if we could see Gaia as having some traits of an anticipatory system. So what it means, it must have some coding. And what is the coding? Well, we had some of answers with Ross Rickaby yesterday talk. The genetic capital, the existence of enzymes like the Rubisco enzyme, etc. But we could also speak of the configuration of the continents. All of that has actually a functional effect in the functioning of the Earth system. If at some point this equipment, if you like, doesn't work with respect to, in this case, the internal forcing, which is the human outburst, in that case we can see that Gaia is in danger. So I think we can phrase a parallel between myself being in danger because I'm in a situation which I cannot anticipate anymore, because I'm suddenly in an alien environment, and Gaia being ill-equipped, having not the right learning history, if you like, to cope with a new phenomenon. And I think I would draw the parallel there.
Thank you very much, Michel.
Thank you.